In this video we look at the condition under which a autoregressive moving average model, ARMA model for short, is stationary. ARMA models play an important role in, for example, financial forecasting. We begin by considering the following basic linear filter model, where set t is the value of the time series at time t, at is a random term drawn from a probability distribution at time t. At minus 1 is another random term drawn from the same probability distribution but one time step earlier. This is 2 steps earlier and this is 3 steps earlier. Psi 1, 2 and 3 are just weights, and this pattern goes on forever. We will use a backshift operator, and this means that whenever we multiply a random term at time t with b, we get the value of the random term one time step earlier. So when we use this backshift operator, we could rewrite the basic linear filter model. So at times 1 is this term, at times b is this one, at times b squared is this one, and so on. Stationarity just means that the sum of all weights is less than infinity. So that is psi 1 plus psi 2 plus psi 3 and so on is less than infinity. We then look at an ARMA model, which is just a special case of the linear filter model. And we have that the time series at time t depends on the value of the time series 1 as well as 2 time steps earlier. Also, it depends on 3 random terms at time t, t minus 1 and t minus 2. So phi 1 and 2 are just weights, and also theta 1 and 2. The notation ARMA 2 just means that it depends on 2 lag terms with respect to the time series as well as 2 lag terms with respect to the random terms. And if we just move these 2 terms to this side and use the backshift operator, we get this expression. So this is the same thing as this one. If we then divide this side by this part of the expression, we just move this one here and we get this one. And now we can compare the ARMA model with the basic linear filter model. So this is this part is here and this part is here. And if we divide both sides by at, we get this expression after we have multiplied both sides by this denominator. So this one is just moved here when we multiply on both sides. Now, in order to determine the relationship between the linear filter model and the ARMA model, we just compare the terms in front of each b on both sides. So for example, here we have b times theta 1, this is this one, and here we have 1 times phi 1 b, so we get this one, and then we have this one times this one and we get this one. And if we do the same thing for b squared, we see that this one goes here and this one times this one goes here, this one times this one goes here, and this one times this one goes here. And if we continue to just compare the terms in front of b, we have this pattern which goes on forever. So we see that this is a homogeneous linear recurrence relation. So this part is just the same thing as this part. So in order to solve this linear recurrence relation, we use a standard technique. We set Cj equal to C times R to the power of j, where both C and R is not equal to 0. So this is just the same thing as this one, and if we use this expression, we get this one is equal to this one because we have j minus 2, so therefore we have r to the power of j minus 2. We do the same thing for j minus 1, and this one is this one, and therefore it's equal to this one, which is here. If we then divide both sides by c times r to the power of j minus 2, we get this expression, which is just a standard quadratic equation. And when we solve this equation, we either get unique roots, two unique roots, which could be real or complex, or we get a double root. And in case we get two unique roots, we just add them and put some constants in front of them. So we have that when the roots are less than 1, this implies stationarity. And then the reason for this is that we have the sum of the weights, all psi, is equal to this expression, because our solution to the linear recurrence relations was this. So if we put this one equal to this one, we get this expression. And from the triangle inequality, we have this expression is less than this expression. And then we have two geometric series, which will be less than infinity whenever the roots are less than 1. So we have found that the time series model, ARMA model, is stationary whenever the roots are less than 1, because in that case, as stated, we have that this part is less than infinity, so we see that the sum of all psi weights in the basic linear filter model is less than infinity, which was the condition for a time series to be stationary.